Section 3.5, we're dealing with transformations of functions. We looked at the family of parent functions in our last lesson, and transformations involve moving or flipping, we call that reflecting, or we could do what is called a dilation, which involves changing the size of a particular graph, but not the shape of the graph. In other words, an absolute valued v is going to remain a v, but we might take the original parent and maybe make it wider. So this is a rough sketch. So the red would represent a dilation of the blue original parent, or we could do the same thing, making it narrower or skinnier. So when we take a parent and change its size but not its basic shape, that is known as a dilation. And so we're going to look at, I've broken it up really into three parts. We're going to look at part one in this particular video, or this slide, and the following slides are dealing just with translations, and then we'll talk about reflections and dilations after that. Okay, so I'm just going to jump into some examples. We looked at the parent function y equals x, which is a line. I'll just do a rough sketch here. A line that goes through the origin, has a slope of 1. And what we're doing here, by adding this number, this constant called k, we're indicating a vertical shift. So, for example, if I start with the parent and say do +2, then all of the points on the parent get shifted up 2 places. Now, with this example, when I say minus a k number, I'm shifting downward. I'm taking the original parent and I'm moving all the points on the parent down 5. Okay, and draw the line from there. So pretty much with the parent y equals x, it's going to be either a vertical shift upward or downward. And that's really pretty much all you have to worry about. When it comes to absolute value, the absolute value v, the parent, of course, looks like this. And my first example here, where I've got this number k that is outside of the absolute value walls, that indicates a vertical shift. So it's like taking this absolute value parent v, and we'll just do an example. If I add something outside of the walls, then I'm taking this parent v and I'm shifting, in this case, 3 units up. If I subtract, let's do in red, now I'm taking the parent v and I'm shifting all the points on it 2 units down. So pay attention to the placement of a number, in this case outside, indicates vertical. Plus a number means up, the y-axis. Down a number means, or negative means down. Okay, now I've got this number I've labeled as h. Just think h horizontal. And if you see the number that's added or subtracted inside the absolute value walls, that's going to indicate a horizontal shift. And this one's a little tricky. You got to be careful, because, for example, this means that h in my, if you want to call this the definition of the horizontal translation, there's automatically a minus sign in that equation that represents the shift. Well, h, in order for this to become +4, the actual number h must have been -4, because x minus -4 would create plus. And it's the h number that tells us how to move left or right. Well, in this case, h was -4, so I'm moving the parent v 4 places to the left, even though in the equation itself, in the function, it looks like it might move to the right. So it's the horizontal shift that you really have to be careful about. Let's go the other way. If I were to do x, absolute value of x -3, then that's taking the parent v and moving it 3 places to the right. Because if you compare h and my red function here, h is 3. 3 being a positive number means I'm going to shift 3 places to the right. Alright. I've got here the parent y equals x squared, but let me just go ahead and say that this also applies to a new parent that we talked about. We didn't mention it in Algebra 3, y equals x cubed. So what I'm doing, the parent looks different, but the translation principles work the same. Okay, remember y equals x cubed is that real skinny S-type shape. So if you know the parent, then the translation moves should be pretty easy. But I'm just going to do y equals x squared. That's this parent parabola. And 2, 4, negative 2, 4. So we'll just say those are the points on the parabola. And now again, just like with absolute value, pay attention to whether or not you're adding outside or no parentheses, in this case inside, and that'll tell you whether you're shifting up or down, as is the case here. And this inside number, since it's inside the parentheses, tells me I'm shifting horizontally, and this is the one you got to be careful with. So for example, taking y equals x squared plus 3, I'm moving all of the parent points 3 places up. Y equals x squared minus 4, I'm taking the parent and I'm shifting it 4 places down. Okay, over here I've got a horizontal shift indicated by this number called h. So once again, if you see this, h is literally negative 3. So this is a shift of 3 to the left of the parent, the u. And then if you see, change colors, y equals x minus 5 quantity squared, then this is a shift of 5 to the right, because the number h, which is positive 5, indicates which way I go and how many. Alright, so if you put them together, we refer to this as vertex form. Let me just give you an example. Okay, so this would be a shift of the parent. Okay, it starts with that parent y equals x squared. This would be 2 places to the left and 3 places down. And we would draw the parabola from there. Okay, and remember, vertex form means that my vertex is negative 2, negative 3. Okay, and again, that does the same thing for y equals x cubed. So let me just, if you have a number that's not involved in parentheses being added, you're shifting the parent y equals x cubed up. If you're subtracting, you're shifting down. When you move that number inside parentheses, we call that number h. Then it acts just like the parabola. You got to be careful. So just to give you another sample, this is moving the parent y equals x cubed 2 places to the left. So the translation rules apply. It's the great thing about them. Once you have them and you understand them, they all apply to all of the parent functions that we're going to learn. All right, and let's see. We ran through some examples. This would be a shift of the parent y equals x squared 3 places up. We'll say 3 units up. This is the parent y equals absolute value of x 5 units down. This is y equals x squared shifted 8 to the right. And this is y equals the absolute value of x. Shouldn't have put 8 there, squared. This is y equals the absolute value of x 2 to the left. All right, so works also for, we haven't touched on the square root function, but let me just make sure we apply it to that. Y equals the square root of x minus 4. You notice how I'm subtracting 4. This would be like inside parentheses, inside absolute value. This would be the parent y equals the square root of x 4 places to the right. Okay, this would be the parent y equals the square root of x 3 places down, because it's like this. I'm doing the operation outside of the square root. Okay, and then we could put them both together. If I did plus 2 minus 3, then this is left 2 down 3. Okay, so that's pretty much a quick run through of translations. And so now let's talk about let's go to reflections. Okay. Got a different set of slides for reflections. When you see the word reflection, you can think flipping over a particular axis. And the whole point of this is to help you understand whether or not you're going to be reflecting over the x-axis or the y-axis. And I'll just give you a couple of examples, and then I'll show you what it really boils down to. If you notice that here I have the parent y equals x squared, but the minus sign, when it's not involved in parentheses, means I'm always going to reflect here. This is the parent y equals x squared reflected over the x-axis. Alright, so this would be taking the parent and basically flipping it over so that it opens down, just flipped over the x-axis. Okay, contrast that with, you notice now the minus sign has been moved inside parentheses. Well, now it's going to be reflected. This is the same parent, but anytime you see minus moved inside parentheses, now it's going to be reflected over the y-axis. So it's all about the location of the minus sign. Okay, inside parentheses or absolute value or the square root function, it's always going to reflect over y. If it's outside, then it's going to reflect over x. Okay, here's some other examples, and let me just add to this list because there are some other parents. Okay, all of these represent flips or a reflection in the x-axis. The key is the negative number is outside when there are grouping symbols or radical. When we move that number inside, and that includes the square root function, that would include the cubic function. Now we're going to get a reflection in the y-axis. Okay, so it's all about the positioning of the minus sign. And that's pretty much all I wanted to cover with you. I think that'll help when you go to do your homework. So now let's talk about dilations. Okay, again, dilation means we're basically changing the size but not the shape. And there's really 4 different ways to dilate these parents. And I want to talk about vertically changing. We call these 2 moves vertical stretch versus vertical compression. When you think of vertical stretch, just think about grabbing the top of maybe like the parent V. If you grab the top of it, if it were kind of flexible and you just started pulling on it upward, you're going to make it skinnier, okay, if it had that kind of flexibility. So think of vertical stretch as a way of taking the parent and basically you can use the word making it skinny, okay. As you stretch it upward, these 2 arrows kind of get closer and closer together. That's what vertical stretch is, and you'll know you have vertical stretch when you have this scenario. You notice that I've got a number that's greater than 1 in front of the absolute value of x, in front of x squared. Okay, that would also be true for this particular case with our square root function. We could also add the cubic function. I've got a number. Key is it's greater than 1. Okay, in the front of any kind of grouping symbols, or in this case the radical sign. I've got vertical compression when that number becomes between 0 and 1. Okay, it's still in front, so you can kind of categorize the vertical either stretch or compression. You can think of compression as starting with the parent V, for example, and just imagine that you're going to push down from the top. If you were to apply pressure from the top, and it would make it become fatter. The pressure from the top would cause it to get wider. Okay, that's what vertical compression is all about. And you notice the difference is when we put a number still in front, but now the number is between 0 and 1. Okay, so for the number that's greater than 1, we're going to have vertical stretch. For the number between 0 and 1, we're going to have vertical compression. Okay, so maybe it works a little bit opposite of the way you think it might. Taking this parent y equals x squared, just doing a rough sketch, if that's the parent, multiplying by 4 actually makes it skinnier. And some people might think, well, I would think that multiplying by 4 would make it much bigger, but it actually has the opposite effect. Multiplying by 1/4 actually makes it more bowl shape, more wider. So I just wanted to get a taste. I don't think we're going to deal with the horizontal stretch and compression because it is going to come up. So let's just take a look at those. It really amounts to the positioning of these numbers. Okay, notice that for vertical, we're outside. It's just that greater than 1 means stretch. Between 0 and 1 means compression. Excuse me. When it comes to horizontal stretch, now we're moving, or compression, we're moving that number inside. Okay, so now notice the scenario when we have horizontal compression. Really, you can think of horizontal compression as vertical stretch. And you can think of horizontal stretch as vertical compression. Okay, they're kind of, in other words, if I take the parent V shape and I stretch it this way, which is what this means, stretch it horizontally, that's really another way of explaining what we did earlier with pressing down vertically, compression. So it's just another way of writing it. When we have this fraction inside the grouping symbols, like we have here, that's going to be an example of horizontal stretch. When we move the number greater than 1 inside the grouping symbols, this is going to be an example of horizontal compression. Okay, I thought I would try to do a couple of homework examples for you. Okay, so since you're watching this, I'm going to go ahead and do a couple of homework problems. So let's just take a look at number 26. The directions on 26 in that block of problems tell us to write the function whose graph is the graph of y equals x cubed. So in other words, so the parent function is this cubic function y equals x cubed, but we're supposed to do a horizontal stretch by a factor of 4. Okay, well, in the previous slide we gave you some examples of how to accomplish horizontal stretch. We have a number between 0 and 1, and it will be placed inside grouping symbols like this. Now I'm showing the quadratic parent, but that's also true for the cubic, which we're about to do. And if we want to accomplish horizontal compression, then we have a number greater than 1 that will be inside grouping symbols. Well, so this is a little bit tricky because we're showing horizontal stretch as a number between 0 and 1, but this says to do horizontal stretch by a factor of 4. Well, in other words, what we're going to have to do to accomplish horizontal stretch is we're going to have to use 1 over 4 x to the third. And notice for horizontal moves, whether it's stretch or compression, we move that number, that coefficient, inside the parentheses. So this would be okay. This would probably be a better way of writing it. If you raise 1/4 to the third power, you get 1 over 64, and then x to the third. So this would be your answer for number 26. So let's take a look at number 28. And these problems, we're starting with the graph of the function y equals the square root of x. But then we're supposed to do certain transformations. So let's just take them one at a time. For part 1, it says to reflect it about the x-axis. Well, to accomplish that, we place the minus sign in front of the radical. Part 2 says, part 2 tells us to shift right 3 units. So we take what we've done in part 1, and to show shifting to the right 3, we're going to do minus 3 under the radical. Okay, that takes care of part 2. And then part 3 says, okay, with those two things done, now let's shift down 2 units. So we just build on what we've done previously. So to take that and move it down 2, then we show minus 2 outside of the radical. So this would be your answer for number 28. I'll just give you a heads up on number 27. You're going to be reflecting about both the x-axis and the y-axis for that square root function. So remember, this gives you the reflection over the x-axis, and then when you do this inside the radical, that gives you the reflection about the y-axis. Easy for me to say. All right, so just want to give you a heads up because you're going to run into that on number 27. I hope that helps. We will work on this. Check it out tomorrow.